Gaussian elimination is a method of solving systems of linear equations. The first step is to get it in echelon form. Echelon form is characterized by this diagonal of ones and triangle of zeros. Here are a few other examples of echelon form. Another very standard example. Diagonal of ones, triangle of zeros. Sometimes there will be gaps, and in those cases we just do the best we can. Here's a gap, and then here's another gap. But still, this is in echelon form. Look at this lumpy triangle. And in all cases, in getting stuff into echelon form, this part is just completely ignored. We don't care about that. Whatever that stuff is, it is. In the case where you got a row of zeros, you just move those to the bottom and ignore it. Here's echelon form. And the usefulness of this can just be easily seen when we solve a problem. Here's a system of equations: x plus y plus 2z is equal to 9, 2x plus 4y minus 3z is equal to 1, 3x plus 6y minus 5z is equal to 0. So when solving for these types of system sets, what I'm going to do is try to get it into that echelon form. So manipulate this matrix in any way I can to get it as close as possible to that diagonal of ones and triangle of zeros. So here I'm going to look for ways of making these three terms 0 and these 1. I don't necessarily have to make these 1, it's just a lot easier to solve this by making these 1. First thing I'm going to do is multiply row 1, this top row, by minus 2 and then add it to the second row. Here, this is positive 2. If I add negative 2 to it, I'll get one of my zeros. I do that. I got my first 0. I can get a 0 here by doing the same type of thing, multiplying the top row minus 3. Now I have 2 zeros. And all of these just add normally. Now I've got a situation where I can't really use row 1 anymore, because if I use row 1 to try to eliminate this 3 right here, then I will be adding to this column again over here, and then I've got a problem back to where I started. So this is where it makes sense to manipulate the matrix again in order to get 1s here, because 1s are easy to deal with. I just multiply it by whatever the other number is. So multiply row 2 by 1/2. Now I've got a 1 there. And it becomes a lot easier to deal with. Now I just multiply row 2 by minus 3, and that will eliminate this one right here. And there are the triangle of zeros. And I don't necessarily need to change this to a 1, but I did it anyways. Just multiplied row 3 by minus 2. There are the diagonal of ones, triangle of zeros. So here it will become apparent why we went through all this trouble to do this. If we put these back into ways we're accustomed to seeing it in variables, x plus y plus 2z is equal to 9. This did not change at all. But let's have a look at these eliminations that we did. 1 minus 7 over 2 minus 17 over 2, 1 and 3, this is y, minus 7 over 2z is equal to minus 17 divided by 2, and z is equal to 3. So I've put it into its simplest possible form for solving for the individual variables, and what it's given me is a solution to one variable, and then in the row above it it's as simple as possible, and in this case, it only has one extra variable. This has one variable, this has two variables, this has three variables. But since I have the solution for one variable here, this becomes a one variable problem because I know this variable. And then this becomes a one variable problem because I know the other two variables. So it's easy for me just to start at the bottom, substitute this in to the row above it, and then substitute that into the row above it. So z is equal to 3. I've got 1. Y minus 7 over 2z is equal to minus 17 over 2. Z is 3. 21 divided by 2. 17, so this difference of 4, so it'll be positive 4, or, well, positive 4 divided by 2, so 2. Now I've got both of these ones. Z is 3, so that's 6, y is 2, that's 8, 9 minus 8, x is equal to 1.